We've talked about generative models before, specifically in case number TCM003005, where we introduced the general idea of diffusion models. They learn to generate complex data by reversing a noise-adding process.
Right, the idea of gradually turning noise into structure. But the examples we saw then were sometimes smaller or less detailed. What changed to get us to the stunning images we see today?
That's where this paper comes in, Denoising Diffusion Probabilistic Models, or DDPMs. This paper by Ho et al. Really solidified the practical approach to diffusion.
So DDPMs are a specific type of diffusion model that made them really work well for image generation?
Exactly. They demonstrated high-quality image synthesis that was competitive with or even surpassed other leading generative models at the time. This was a significant leap.
And this denoising part, is that the key to the quality? Are they essentially just getting really good at removing noise?
Yes, it is. The core idea is that images are generated by reversing a process that adds noise. Think of it like taking a perfectly clear image and gradually blurring it until it's pure static.
And the model learns to unblur it step by step, starting from static. So it's learning the opposite of a blurring process?
Precisely. The paper calls them latent variable models inspired by considerations from non-equilibrium thermodynamics. It sounds complex, but the intuition is simpler. Diffusion, like heat dispersing, is a natural process.
Like how ink spreads in water, or a smell fills a room. It's easy for things to become more disordered, but reversing that flow is hard.
That's a perfect analogy. The challenge and the genius of DDPMs is learning to unspread the ink or undisperse the smell step by step to create specific images. Let's see how that works.
I'm ready to dive into that. How do they actually formalize this noise adding and then reverse it?
This blog post by Lillian Wang explains it beautifully. The forward process is simple. We define a Markov chain of diffusion steps to slowly add random noise to data.
A Markov chain means each step only depends on the previous one, right? Like a game of telephone where the message gets progressively garbled.
Precisely. Starting with an image, say x0, we perform a forward diffusion process in which we add small amount of Gaussian noise in t steps, creating x1, x2 till xt.
And the key is small amount. It's not one big jump, but many tiny increments of noise, gradually destroying the image information?
Exactly. As the text states, the data sample x0 gradually loses its distinguishable features. Eventually, xt is just pure Gaussian noise.
So xt is just random static, like a detuned TV? This forward process seems pretty straightforward. The magic, I imagine, is in reversing it. The blog says they learn to reverse the diffusion process to construct desired data samples from the noise. But how do you unnoise something?
That's the core challenge. If we knew exactly what noise was added at each step in the forward process, we could just subtract it. But we don't.
The difficulty lies here. If we can reverse the above process and sample from q of xt minus 1 given xt, this means predicting the slightly less noisy image from the current noisy one.
It seems like an impossible task. You're trying to guess what structure existed underneath the noise without ever having seen the original structure for that specific noisy image.
You hit on the critical point. We cannot directly calculate the exact reverse. Instead, we need to learn a model p theta to approximate these conditional probabilities.
A neural network, I assume? One that takes a noisy image and tries to predict what it looked like a tiny bit less noisy?
Exactly. The goal is to start with pure noise, pass it through this learned model t times, and recreate the true sample from a Gaussian noise input. Imagine a sculptor starting with a block of raw clay.
And the model, step by step, chipping away tiny bits of noise to reveal the image, like the sculptor refining the clay. It's iterative refinement.
Yes, that's the core intuition. Now let's explore how DDPMs train this sculptor model. What specifically does it learn to predict to make this denoising possible?
I'm curious about the what. Is it predicting the clean image or just the noise itself?
So we have a neural network that needs to learn to approximate the conditioned probability distributions in the reverse diffusion process. The question is, what should this network predict?
Does it try to predict the original x0 from the noisy xt? Or maybe the xt-1 directly?
Instead of predicting x0 or x of t-1 directly, DDPMs found it more stable and effective to reparameterize the Gaussian noise term instead to make it predict epsilon t.
So the neural network takes a noisy image, xt, and a time step t, and its job is just to predict the exact noise that was added to get to xt?
Exactly. It tries to predict epsilon t from the input xt at time step t. Think of it as a very sophisticated noise-canceling headphone, but for images.
If it can accurately predict the noise, then you just subtract that predicted noise from the noisy image, and you get a slightly cleaner one.
That's the core mechanism. The model learns by minimizing a loss function. Initially, the objective is complex, comparing distributions.
So the network is trained to get as close as possible to the actual noise that was added at that step?
Surprisingly, the original DDPM paper found that training the diffusion model works better with a simplified objective that ignores the weighting term.
Wait, they simplify the loss and it works better? That feels counterintuitive. Less precise math gives better results?
It's a common empirical finding in deep learning. Sometimes simpler objectives lead to more stable training or better generalization. This final simple objective is essentially just an L2 loss.
So it's literally just mean squared error between the actual noise and the noise the model predicts? That's remarkably simple for something that generates such complex images.
Let's say we have an image x0. We add a known epsilon noise to get x1. The model sees x1 and tries to predict epsilon t. If it predicts epsilon prime close to epsilon, its loss is low.
Then, during generation, it starts with pure noise, runs it through the model, gets a predicted epsilon, subtracts it, and repeats until it has an image. Got it.
This mechanism, predicting noise with a simple objective, unlocked unprecedented quality. However, it still operated on raw pixels, making it computationally very expensive. That's where latent diffusion models come in.
Pixel space is huge, so there must be a way to make this process more efficient, especially for high-resolution images. If DDPMs operate directly in pixel space, does that mean a lot of computing power is wasted on details that might not be perceptually important?
Precisely. Imagine a 1024 by 1024 image. That's over 1 million pixels. Running a complex neural network over that many dimensions, step by step, for hundreds or thousands of steps, is incredibly slow. This paper highlights the problem optimization of powerful DMs often consumes hundreds of GPU days. That's a massive barrier for many researchers and applications.
Hundreds of GPU days just to train? That's not practical for rapid iteration or widespread use. There has to be a more efficient way.
The solution proposed by latent diffusion models, or LDMs, is to apply them in the latent space of powerful pre-trained autoencoders. This is the core innovation.
So instead of diffusing pixels, they diffuse something else? What does latent space of autoencoders even mean here?
Think of an autoencoder as a compression algorithm. It learns to take a high-dimensional image, compress it into a much smaller, latent representation, and then decompress it back into an image.
Like a zip file for images, but instead of losing data, it learns to keep the important information, just in a more compact form.
Exactly. The autoencoder handles the complexity reduction and detail preservation. The diffusion model then operates entirely within this compressed latent space.
So the diffusion model sees a much smaller, more abstract representation. It's like blurring and unblurring a mental model of the image, not the raw pixels themselves.
This efficiency gain then opens the door for powerful new capabilities. LDMs introduce cross-attention layers into the model architecture for conditioning.
Cross-attention. We know that from the transformer architecture in case number 153005. So they're using attention to link the latent diffusion process to external input?
Yes, now the diffusion model can be guided by text or bounding boxes. You can type a prompt like, "a majestic cat sitting on a cloud," and the cross-attention mechanism steers the generation.
This is what enables those incredible text-to-image models. The latent space makes it efficient, and attention makes it steerable by language.
The result is significantly reducing computational requirements compared to pixel-based DMs, making high-resolution, high-quality, and highly controllable image generation accessible.
So, whenever I see a diffusion model creating amazing images from a text prompt, I'm now thinking autoencoder, latent space, and cross-attention.
Exactly. LDMs show how combining foundational ideas like autoencoders and attention with the core diffusion process can lead to breakthroughs in capability and efficiency. It's a powerful framework.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.